Hello everyone, am I audible? Sorry for the delay today. We kind of got delayed by 30 minutes. But anyways, let us begin. So today is the day 8 and we are going to solve linked list today. Mm, Just a moment. Cool. Hi again everyone. Let me just see if there are any comments. Okay, so many people are asking me to use Java. I actually have never done competitive programming myself in Java. I normally do always in C++. But what I can do is, from the next lecture, I can share you the codes that I did, their counterpart in Java as well. Will that work for you people? Because I personally do know Java, but I have never really coded in Java that much for competitive programming. So my hand is not, what do you say, completely stable with it. Okay, cool. So just give me a moment and we will start. And yeah, I'm not seeing. So which questions do you want us to solve today? Because like linked list is a very basic topic. It looks like a basic topic. So I'm leaving it upon you. What are the questions that you want me to solve? So it's totally live stream and how many questions you want. And today we will do it. Let us do one question from each of these topics. Will that work for you all? Like do a very big kind of, what do we say, session and we do a lot of questions today. Is that working with you? Cool. So we will start with the very first bucket. So what I have decided that from each bucket, I will be doing one question. Okay. So let us start. So hmm, let us do the very first question from each of the buckets. Okay. Okay. Let us start with the palindrome list. So the question says that we are given a singly linked list and we have to determine if it is a palindrome or not. If it is a palindrome, return 1, or basically if you do Boolean, it is true for 1. And if it is not a palindrome, we return a 0. So like in Boolean, false represents 0 and true represents 1. So basically we have to return true or false if we talk in parallel sense of a Boolean variable rather than an integer. Okay. Okay. So and the solution that is expected is linear in time and constant in space. Okay. So now let us assume that hey, this time we are given a linked list. Okay. So suppose you were given an array 1, 2, 3, 4, 3, 2, 1. This is a palindrome, right? How can we find if it is a palindrome? We can start a pointer from the left side and similarly a pointer from the right side going towards left and a pointer from left side going towards right. At each index, we check. So for example, at the very first stage, left will be this, wait a moment, and right will be this. Is the pointer at left equals to the pointer at right? Yes, it is equal. So now that means it satisfies the property. We increment a left and we decrement r. Is the new left and right equal? Yes, they also are equal. So we again increment L and we again decrement R. They are also equal. Then we increment L and we decrement R. This time L will be equal to R. So like L and R both will be together. Okay, so at this stage we can stop because this is a central point. Okay, so if it had been an array, we could have done something like this: int L equals to 0, int R equals to n minus 1, while L less than R. If AL not equal to AR, return false, else we do plus plus L minus minus R, and when we are out of the loop, we can just return true. That means that the array was sorted. But this thing doesn't work well for a linked list. Why doesn't this work well for a linked list? Because in a linked list, we don't have random access. We can't directly assess this number and this number. Similarly, a singly linked list doesn't allow you to go backward side. It only allows you to go the next side. Okay, so this is why we can't use exact same approach for the linked list. Okay, but now let us see this. That let us say this was a linked list. Okay, check it. If we also reverse this linked list, what will happen? If we reverse this linked list as well, then the reverse of this linked list will also be 1, 2, 3, 4, 3, 2, 1, right? So we can see that for a palindrome, the linked list and the reverse of the linked list is equal. Okay, so I mean, like, if we are somehow able to reverse a linked list, we can find if a linked list is palindrome or not. Okay, now the question comes, how will we find if, how will we reverse a linked list? Okay, let us see how we can reverse a linked list. Okay, so linked list is something like this. 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, which is pointing to 3, which is pointing to 2, and finally this is pointing to 1. Okay, now suppose at every iteration we are maintaining 3 pointers. This is the previous pointer. Wait a moment. This is the previous pointer. This is the now pointer, and this is the next pointer. Now, what we see that in the reverse of the linked list, now next will be what was previous element, and next, so basically now next will be the previous element. Okay, okay. Now let us do exact same thing. Let us try to use this approach to reverse the linked list. Okay. Uh, so Gaurav has asked how to open this particular page. Gaurav, you can click on this link. I post some comments. Okay. This is the practice section on interview page. Okay. Cool. Okay. So now, if we somehow are able to reverse the linked list, and how to reverse the linked list we already know, then we will be able to, what we say, then we will be able to find if a linked list is palindrome or not. Okay. Now, from what index should we reverse? Actually, we should reverse only this part of the linked list, right? Because when we reverse this part of the linked list, the linked list will become 3, 2, 1, and whatever comes after this doesn't really matter to us. Sorry, if we reverse this part of the linked list, this will change to 1, 2, 3, and whatever that comes after this doesn't matter to us. We will keep on comparing each element. So 1 is equal to 1, okay, 2 is equal to 2, and 3 is equal to 3, and we are done. Okay, so we will reverse the part of the linked list that comes after the middle element. Okay, let us do that. So the first question comes out is, first we have to find the middle element. Okay, then the second thing is reverse the list after the middle element. Okay, and then we have to compare corresponding elements in the first half and reverse of second half. Okay, now let us do this step one by one. So how will we find the middle element? So I mean, like, if you have not heard of this approach, this is known as hare and tortoise approach. Okay, what a hare and tortoise approach is that we maintain 2 pointers on the linked list. Initially, the first pointer is here as well as the second pointer is here. one pointer moves faster, actually at the double speed of the second pointer. Okay, so at the next step, the first pointer will go here, the second pointer will be here. Then in the third step, first pointer will be here, second pointer will be here. Then first pointer will be here and second pointer will be here. So as soon as one of the pointers reaches the end of the linked list, that means the other pointer will be at the halved position of the linked list. Okay. So I mean, like, you can read about this after this session if you are hearing this approach for the very first time. But let us do that. So we say list node value at tortoise. I mean, you should actually not take these variable names. You should say slow, which is initially A. Then you should also say fast, which is equal to A. Okay. So while fast not equals to null and fast next not equal to null, so we move the slow pointer by one step. Slow is equal to slow next. But we move fast pointer by two steps. Fast is equal to fast next next. Okay. Now, when the fast will be null, so when the fast will be null, that will be a situation like this. Let us say this is a linked list. So in this case, initially slow will be here and fast will be here. Then fast will go here and slow will go here. Then fast will go here and slow will be here. So when the fast is null, at that time, slow is pointing to the first element of the second half of the linked list, right? Okay. But let us take a case when the linked list is of odd size, 1, 2, 3, 4, 5. In this case, initially slow is here, fast is here, then fast goes here, slow goes here, then fast goes here, and slow is here. At this point, slow is pointing to the exactly middle element. Okay, and we have to reverse the second part. I'm like just after the middle element. Okay, so we will say if fast not equal to null, slow is equal to slow next. Now we are sure that the element slow is pointing to the very first element of the what we say linked at the very first element of the second half of the linked list. Okay, awesome. But anyways, we will have to do, wait a second. Slow if fast not, okay, and if fast not equal to null, second is equal to second next. Okay, that's it. And always we have to set this slope next equals to null. Now we reverse the two linked list. Sorry, now we reverse the linked list that starts at second. Okay, how will we do that? We say list not. So this is also a very good technique that you should use whenever you are solving a linked list problem. While solving a linked list problem, you maintain a dummy head. Okay, which is a node that contains only 0. So initially, the previous will be dummy. The current will be the very first node, which is A, and next will be nothing. So we will say while now not equal to null. Okay, next is equal to now next. Okay, then now next is what? Now next is the node that was the just previous node. Okay, so actually we can actually initially take previous as null. So that will also work for this. Okay, now next is equal to previous. And now what is the previous? Now previous is equal to now. Clear? Okay. So now we have done this. At the end, the previous node will represent the head of the new list, because at the end, previous will point to the node 4, which is the new start of the list that comes at the second half. Okay. Okay. So now we know this. So we will say while Your first pointer is at A and the second pointer is at previous. And we will say while first pointer not equal to null and second pointer not equal to null, if first pointer key value um, yes is not equal to second pointer key value, return false, and we say pointer equals to first pointer ka next and second pointer equals to second pointer ka next. Finally, if we are out, that means we can return true. That means the whole list was a palindrome. Does this seem correct? Hmm. Let us test it. No. Okay, so actually we did a time limit exceeded. So basically we entered in some kind of a loop, right? Let us see where we did wrong. Initially the slow is A and fast is also A. We say while okay, fast is equal to fast connect, okay. Second is equal to slow, and we say slow connect is equal to null. Okay, so we should do this here because otherwise we already have something like this, right? Let us see if we can test it. So we are saying while if fast not equals to null, second is equal to second ka next, okay, and we are setting the slow connects to null. Slow is the previous element, okay. Hmm. So in this case, in the very first case, we saw that when fast was null, slow was pointed to the first element. So we also need to know actually the previous. So we also need to know the previous slow which will be initially null, and we will say previous slow is equal to slow. Okay. So okay, in this case, when the array size is even, initially slow will be here and fast will be here. Okay. Then slow goes here, fast goes here, slow goes here, fast goes here. In this case, previous slow ka next should be null. Okay. Else, mm, else previous slow ka next should be equal to null, and second is nothing but slow. Okay. Great. But in the case of odd, slow will point to the very first element. So second is equal to slow ka next. Okay, second is equal to slow ka next, and we set slow ka next equals to null. Okay, now does this look cool? This looks good. And so here we are breaking the list basically into two parts, and then let us see that if we can actually test it. Hmm. First, let us test in custom input. Interesting. What is happening? So we are saying that list node value at A is okay. We point slow here with previous is okay. While fast not equals to null and fast connects not equal to null. Previous slow is the current value of slow. Perfect. We say slow is equal to slow ka next. Okay. Fast is equal to fast ka next. Okay. Okay. So in this case, fast will be null. Okay. And we start sorting from here. Okay. We say while now not equal to null. Are we ending here? Because we are entering into a loop, right? So we are saying while now is not equal to null. Currently now is A. Next is equal to, okay, we are not changing now to next, right? Previous is now, but now is also next. So we have to do this. Okay, and now this will work. Yep. So, but this case it should return 1, right? So in the case of 1 2 1, slow will be here and fast will be here. Then fast goes here and slow comes here. So in this case, what is the start of the next? This is 1. So we will say that we have to reverse the list that starts at second. So we have to reverse this thing, right? While now is not equal to null. Now is actually not A. We are reversing the first list. Now is second. Okay. So now this should work. Yep. Now this is working. Yes. And let us submit it. Are we missing an edge case? I think yes. We probably are missing the edge case where all the elements are null. So one advice for any kind of linked list question, make sure that you never end up assessing a null element. That is actually a very big mistake that many people do. Okay. Always ensure that the pointer that you are assessing in a linked list is not null. So that is one of the biggest mistakes I've seen many people doing that in linked list questions. Okay. Cool. So we're done with the very first question. So here we learned two techniques. The one was the hare and tortoise approach, and the second thing was how to reverse a linked list. So basically, this is a combination of two questions. Let us do a question in this pointer now. So let us say that we are doing swap list nodes in pairs, okay? Because K reverse linked list is just same as the normal linked list question, normal reverse the list question, okay? Let us say that we are solving this question that is swap list nodes in pair. Okay, so we are given a basically linked list and we have to swap 1 and 2. Then we have to swap 3 and 4. So basically 1 and 2 will become 2 and 1. Then we are done with this particular part. Now we are taking the care of the part 3 and 4. We again the swap it which becomes 4 and 3. Okay. And we are asked that hey, we have to use only constant extra space. So basically, we can't create a new linked list. But what is meant by a constant extra space question is normally that what we mean by a constant extra space in linked list is that you don't have to create a duplicate node. You have to use the nodes that were given in the initial question itself. Okay. Yes, Tosif, I think in the previous question, P slow was not required. At the end of this video, I will again go back to the question and then we will try to improve it, okay? Because I think I kind of messed some parts of it. We will go back after we are done with today's video, okay? Sure, Gaurav, I will summarize it at the end, okay? I mean, like after I'm done with two more questions and then we will shift. Reorder list. I think you're talking about what the next question we should do, right? I will see that. Okay, anyways, let us try to see how we can do this. So basically, linked list is nothing but a game of pointers. How you are able to mingle pointers is how you will win the game. So let us say that we have 1, 2, 3, and 4. Okay. Okay. So now suppose I have to reverse this linked list. Here, actually, you will. So I told that in the previous question as well that dummy head is a very common and helpful technique in solving any kind of linked list question. Okay. So, for example, here what I will say, I will assume that there is a dummy node here, after which it is 1, after which it is 2, and 3, and 4. Okay. So now see, suppose I am reversing the pair of 4 and 3. Okay. Suppose I am reversing the pair of 4 and 3. I at least need the pointer to 4 and also the pointer to 3. Okay. But I also need the pointer to 2. Why? Because when I have reversed these two, I have to make sure that 2 का next points to 4. ठीक है? So we at least need 3 pointers. Okay. ठीक है? So let me first create a dummy node. Okay. Okay. let me name this pointer. Let us say that when we were swapping 3 and 4, let me name the variable 2, the variable that stores the node 2 as the previous pair end. Okay, so let me say list node value at previous pair end. Initially, it will be dummy, right? Because this is the end of the first pair. So as assumption, this is our assumption. Okay, so this will be dummy. Okay, this will be equal to the current pair start. Okay, so this is mm, current pair start. Okay, which is in the case of in the first case, this will be the node A itself. Okay, awesome. Okay, so while I will say that while the start of current pair is not null, start not equal to null. Okay, so I will say current pair second is equal to okay. I let me also assume that current pair start ka next is also not equal to null. Is not equal to null. Okay, so current pair start ka next. So basically, both the nodes of the current pair exist. Okay, if there is only one node, we don't need to do any swap, right? So I will say current pair second is equal to current pair start ka next. Okay. Okay. I also know the previous pair end. At the end of the current iteration, what will be the previous pair end? Previous pair end at the end of current iteration will be the starting node of the current pair, because at this time, let us say this was the start and this was the end. Okay, so after this will change to 4 and 3. So basically this will be the previous pair end, so which is the current start node. Okay, okay, and we also have to make sure that current pair ka second, so basically previous pair end ka next is equal to current pair second. Why? Now has to point to 4. Okay, and current pair second ka next is current pair start. So now we have made sure that 2 points to 4, 4 points to 3. Okay, and finally we have to make sure that 3 points to this. Okay, so current point start, current pair start ka next should be equal to what is currently the current pair second ka next. Okay, finally changes the current pair second next, and this is previous pair end. Okay, and finally I can just return dummy ka next. Okay, because dummy was just a node that we assumed. Okay, so now in this case dummy ka next will become, so the pointers will change like this, right? And 1 will now point to 3 and dummy ka next will point to 2. So dummy ka next will actually be 2, which is the start of the next list. Let us see if that is correct or not. We might have done some errors, but let us see. Hopefully not. What did I do? Oh, I didn't comment here. What are we doing here? So we are saying that initially we actually made sure that dummy ka next should be equal to A. Okay, because dummy is going to point to 1, right? That I told earlier. I will like initially dummy should point to 1 and 1 should point to 2. So I didn't point it dummy to first one. Now let us test this. Zero, okay, and I say uh, first pointer previous pair end is dummy, okay, and current pair start is A, okay, while current pair start is not equal to null and current pair start next is not equal to null, okay, both are not equal to null. So then current pair second is current pair start next, okay. We change the previous pair end next to current pair second, okay, so now dummy node is starting to point to 2. Then we make sure we point uh, 2 connects equals to, sorry, 1 connects equals to 3, okay. So now dummy node is pointing to 2 and 1 is pointing to 3, okay. Now we should point 2 to 1, so current pair second connects, that is 2, is now going to point to 1, okay, and previous pair end will be equal to 1, that is fine. So this thing is fine. And what will be current pair start? uh, okay, so now we have not changed current pair start. uh, if previous pointer end not equal to null, current pair start is equal to previous pointer x next, else current pair start is equal to null. Similarly, if current pair start is not equal to null, then uh, okay, so we don't have to do that. So we only need current pair start and we are done. So now 2834 is changed to 3428. 4874 is changed to 7448. Similarly, 4249 is changed to 4942, and we are doing well. Let us see if we have any issues. Seems fine. Great. So we got this as well. So what thing we learned from this thing, the takeaway should be that, hey, for any linked list question, first try to find what are the pointers that you need to know to reorder the list in any way. Suppose it is swapping pair, what are the elements you need to know so that you can change their pointers to something else? That is the very first thing you need to know. And the second thing is, again, I tell you to know, is this dummy thing. This is very important in a lot of linked list questions. I will do one more question after this that will use this thing. And the third thing is, make sure that you are never assessing null. Okay, so here also I do a check of null. Make sure you are never assessing something that is null. Okay, cool. Let us do one more question. Uh, Akash has asked, can we do the reorder list question, right? Let us see that. Okay. So the question is, we are given a singly linked list L0, L1, Ln minus 1 to Ln, okay? And we have to reorder this to L0, Ln, okay? So the very first node from the start and the very first node from the end, then the very second node from the start and the second node from the end, third node from the start, third node from the end, and so on, okay? And we must do this in place without altering the nodes values. So what in place means is that you don't have to change their values. I mean, like, you can dangle some pointers, but that will work. Okay, you just don't have to change the node values or create a duplicate of those nodes. That is the only requirement. Okay, ठीक है. So one thing that I find from here is that, hey, if we somehow, let us say that this was our list, okay, our list was 1, 2, 3, 4, 5, and 6. We have to change this to 1, 6, 2, 5, 3, and 4, right? Suppose I know the first half of the list, I also know the second half of the list, which is 4, 5, 6. Okay. Now I reverse the second part of the list. This is 6, 5, 4. Now what I do, I keep on merging this. First, this is 1. So I will put this 1. Then I put this 6. Okay. Then I put this 2. Okay. Then I put 5 and so on, right? Okay. So how can we do that is first split the list in two halves, okay? Then reverse the second half, okay? And finally merge two lists. This is something that you do. This is something very similar to that you do in a question like merge sort, right? In merge sort, the merge step is something like this, okay? Okay, let us do these steps one by one. In the previous question, we had discussed an approach to split the list in two halves and reverse the second half, right? We had discussed that in the very first question for the day. Okay, so let us do that. So how did we do that? We do this question by using two pointers, the slow and the start. Okay. So initially the slow pointer is equal to A and the fast pointer is also equal to A. Then we do while, while fast not equal to null and fast next not equal to null. Slow is equal to slow next and fast is equal to fast next next. So now there were two cases. The first case was if fast not equal to null. When did that case happen? Let me redraw it again. That case happened when the linked list was of odd size 1, 2, 3, 4, 5. So in this case, slow will be here and fast will be here. Slow changes to this, fast changes to this, slow changes to this, fast changes to this. In this case, fast is not equal to null, right? Okay. In this case, we can reverse this whole linked list. So this will change to uh, 1, 2 will remain as it is, and this will change to 5, 4, 3. Suppose we are able to do that, then we can do the merging, right? Or not. Hmm. Yes, you can do that. So it will be equal yes. Okay. Okay. If the size of the linked list is even, then it will be 1, 2, 3, and 4. Then slow will be here and fast will be here. Then slow goes this, fast goes this, slow goes this, and fast goes this. Then also we can reverse the linked list that starts at start. So that we could do even in the previous question. I missed this thing. So we can reverse the linked list that just starts at the slow pointer. Okay. So suppose we reverse this part of the linked list, then we are cool. Let us see how we will do that. Hmm. So also we have to make sure that we make sure that the pointer of 2 is now the next of 2 is null so that these two lists break off, right? Else anything can happen. So we will say list node value at previous low is equal to null and previous low will be equal to slow. So finally we can say previous low for next is null. So at this point, we have broken the list into two halves such that slow points to head of second half. Okay, great. Okay. So now let us reverse the linked list that starts at the slow pointer. Okay, so basically reverts this 345 to 543. So we will say list node value at previous is null, list node value at current is equal to slow, and list node value at next, this variable we will need. We will say that while current is not equal to null, that means there is still a node there. Okay? So while current is not equal to null, I will say next is equal to current ka next. Then I set current ka next is equal to previous. Finally, I change previous equals to current. And what is the next current? The next current is the node that was currently stored in the variable next. Okay, great. So now this has reversed the linked list at 345 to 543. At the end, the node 5 will be the previous node. So we can say that list node value at second head is equal to previous. Now we do have to just merge both the linked list, right? So we will say while a not equal to null, sorry, yes, for this also we will need a dummy node. Okay, then we will need a pointer to the current index in the dummy in the answer. So list node value at dummy pointer, initially it will be equal to dummy. Okay, we also need a pointer which will be initially a, and we also need the pointer to the second half, right? So this will be second head, right? So we say that while a pointer not equal to null and second pointer not equal to null, okay, so while both of these are not null, we first append the second thing to this. I mean, like, then we append, but we say we have to first append the node at a pointer, right? So we say dummy pointer ka next is equal to a pointer, okay? Then dummy pointer equals to dummy pointer ka next. Finally, dummy pointer ka next, okay, and a pointer is also equal to a pointer ka next. Then dummy pointer also moves to one step ahead. We change dummy pointer ka next is equal to b pointer, or the node that b pointer points to. Okay, and then we say b pointer is equal to b pointer ka next. Okay, great. So now what will we be having is, suppose for the nodes of size, sorry, suppose for a linked list of odd size, we will be having something like this: 1, 5, 2, 4. Okay, but at this time, the pointer to the second pointer will not be null, but the first pointer will be null. So we say if second pointer, or if second pointer, there should be second pointer, right? If second pointer is not equal to null, that meant that the total number of nodes were odd. So we will say dp, again we have to make sure, okay, dp next is equal to what we say, the second pointer. Okay, okay, so dp next is the second pointer, and finally we have reached the end, so we don't need to do anything. We can so yeah, we are done. Now where is the answer? The answer is the dummy head ka next, right? Because dummy head ka next is storing the very first node in the answer. So we can just do return dummy pointer ka next, sorry, dummy head ka next, like this. dummy का next. Let us see if this works. What is this happening? This is returning dummy pointer connects. What is the dummy pointer connects initially? This is the first pointer, but the first pointer is null. Initially, the second pointer is also A. So the second pointer will still point to this. So second pointer will not be equal to null. So this should be correct, right? So let us see why this particular case is having issues. So for the list of size 1, only a single node, slow will be 1 and fast will be 1 and previous slow will be equal to null. Okay, so in this case we won't ever go here. So if we don't ever go here, that means that there was only one node, right? That will happen only if there was less than 2 nodes. So we can say if previous slow is equal to null, we can just return the original linked list. Why? Because this thing will happen. I mean, like previous slow will be equal to null only if there are 0 nodes or 1 node. In that case, we don't need to do anything and we can just return the original linked list itself. So now this should work. Yep. Are there any other cases that you are missing? No. So that yes, and let us submit it. Great. So yes, in this thing we missed checking for null one time and we again ended up with an issue. So that is why I was saying that never get to a situation where you are not checking for nulls. Okay. And also again you saw that what is the use of dummy pointer. Dummy pointer allows us to improve the code quality by not checking for nulls in the initial previous. Okay, so use this technique as well. Let us do one more question for the day and then we will end. I think we already have completed the today's streak probably. Yes, but let us do one more question. Okay. What question do you guys want me to solve? Anyone from the linked list section? Anyone? Let us do this list cycle question because this is a very this also requires knowing a technique that many people might not know. So let us do this. Okay. Okay. So we are saying is told that we are given a linked list. We have to return the node where the cycle begins. Okay, the linked list might or might not have a cycle, but if there is a cycle, we have to return the node, the first node from the start where the cycle actually started. So for example, if we start traversing this linked list like this, the node 3 is the very first node where the cycle began, right? So we have to return the node 3. Okay, great. So let us see how we will do that. So see, we once found a middle of the linked list, right? We were once able to find the middle of a linked list using the previous approach, right? So some people are suggesting the hash approach, but if you see the hash approach has a space complexity of order of n, right? So we have to do something that has space complexity of order of 1, but time complexity of order of n. Let us do that. Okay. So we remember that hey, we were able to find the middle of a linked list using the hare and tortoise approach. But if the linked list has a cycle, will we ever be able to find the middle? No, right? Because fast will never be equal to null. So if we start growing from 1, 2, 3, 4, then we will keep on coming back to 3, 4, 3, 4. So if we were suppose finding this thing, value at slow is A, fast is also A. We say while fast is not equal to null and fast next not equal to null. fast is equal to fast connects and slow is equal to slow connects. Okay, but when there is a cycle in the linked list, this loop will never end. Okay, because it will again going on circle around. So let us say what will happen. Okay, suppose the loop is circling around and currently, let us say this is the case. So this is a linked list 1, 2, 3, 4. Okay, okay. And suppose all these nodes are in a cycle. Suppose all these nodes are in a cycle. Okay, it might happen that currently fast is here and slow is here. Okay, that means in the next iteration, fast will go what we say at this place, and where will slow go? Slow will also come at this place. Okay, so okay, that is the case one. The case two is, let us say fast and slow are very much behind. Okay, let us say initially the fast was here and slow was here. Okay, then what is going to happen in the next iteration is, in the next iteration, fast is going to come here and slow is going to go here. Now this condition is again same as this condition, right? The condition that we had here. So we can say that if fast and slow pointers are in a cycle, that means they are definitely going to meet at some time. Okay. So we can say while fast not equal to null and fast connects not equal to null, okay, if fast is equal to null, this means that there is a cycle, right? This means there is a cycle. So we can break. Okay. So here we can say that if fast is not equal to null, or and fast connects not equal to null, or fast connects not equal to null, what do we have to do? Okay, so let me say that I pool cycle is equal to false. If we enter in this loop, we say that cycle is equal to true. That means there is a cycle in this current thing. Okay, so if there is a cycle, now the question comes, how will we find the start of the cycle? But let us solve the case if there is no cycle. If there is a no cycle, we can just return null, right? Now let us see how we will find the start of the cycle. Okay, so let us say our cycle is like this. So there are nodes 1, 2, 3, 4, 5, 6, 7, and this 7 is pointing to let us say 4. Okay, so 7 is pointing to 4, something like this. Okay, so suppose 7 is pointing to 4. Okay, that means this is a cycle. Okay, great. So now how will we find that 4 is the start of the cycle? How will we be able to do that? Let us see. Suppose, assume that this size, the size of the linked list before the start of cycle was A. Okay, okay, suppose this size of the linked list before the start of cycle was A. Okay, and currently both the slow and fast pointers will be traversing 4, 5, 6, 7, again 4, 5, 6, 7, and so on, right? Is that clear? Okay, so now we know that this is, so now somewhere inside this linked list will both these nodes meet. Suppose both the fast and slow meet at this particular place. Okay, and let us assume that from the node start, this distance was B. Okay, so A was the distance of start of cycle from head, and B was the distance of meeting from the current node. Distance of meeting from the uh, from the start of cycle. Okay, okay. And let us say we also have a variable c, which is the start of cycle, which is the size of cycle. Okay, okay. Now, can there be any formula between a, b, and c? Is there any relationship between a, b, and c? Any guesses? Yes, Tosef, that is true. That fast will not become null when there is a cycle that we have assumed. So basically, that is why at this particular position, if fast, uh, wait a second, if fast is equal to slow. Sorry, thanks for pointing that out. If fast is equal to slow, we are saying that there is a cycle. Okay, is that clear? Okay. So now let us try to see of one more thing. We say that hey, this size was A. Okay, this size, suppose the nodes met at node 5, this was, this size was B, and this size is C. Can there be a relationship between A, B, and C? Hmm? Let us say in this way. Suppose the fast and slow pointer had traveled this node x times, this cycle x times, when they were inside the cycle, because they will keep on circling around, right? Okay, suppose they had traveled x times, so the total distance traveled by slow will be equal to this, which is a, plus the number of times they travels this cycle. What will be the number of times? Let us say they traveled this n times, and what is the size of this they traveled? The size of cycle is c, so plus n times c, and they met at this. Okay, so what is this distance? This is b. So this will be the distance covered by the slow node, correct? Okay, and what will be the distance covered by fast node? The distance covered by fast node is nothing but 2 times the distance covered by slow node, right? Okay, but how many iterations would it have done? How many iterations would the fast pointer would have done? Suppose fast pointer did y iterations. Okay, slow pointer had done x iterations, and let us say fast pointer had done y iterations. So the distance covered by the fast pointer is going to be a plus hmm, a plus okay, so this is n, let us say this is m. Okay, so a plus m into c plus b, right? That means a plus m into c plus b is equal to 2 times a plus n into c plus b. Is that clear? Okay. From these two equations, we can find that we'll be able to find that what will be the equation that will come out to be? The equation will come out to be that hey, what is the distance from a plus b? Okay. Okay. So if we try to expand this equation, this will become a plus m into c. So let us try to expand the right hand side first. This is equal to 2 into a plus 2 into n into c plus 2 into b. Okay. If we take b to the left side, so this will become a minus 2 into b. Okay. And also bring this a to minus 2 into a plus b, right? So okay, so this is going to be equal to 2 into n into c minus uh, m into c, right? Okay, so what we get from this is that this is nothing but equal to minus of, this is equal to minus a minus b, and the right hand side is equal to uh, c into 2 into n minus n, right? Okay. But what we find from this means a plus b, a negative, is equal to uh, c times something. Okay. But what is c? We see that c is the size of cycle. So basically, we find that hey, the distance from a to b. So basically, this distance is actually going to be a multiple of the size of cycle, right? So if we again start a pointer from this particular position and we again, so basically till this time this goes till here, the pointer that will be at this place will actually come to 4 again. Why? Because it will go from 5 to 6 to 7 to again 4, and by the time the another pointer, if we start from 1, will also reach to 4, and 4 is going to be the start of cycle. Okay. So what we can do is we can again put slow is equal to what we say a, and we say while slow is not equal to fast, this time we will move both the pointers by only one movement. Okay. So we will say slow is equal to slow connects and fast is equal to fast connects. Okay. Now that means, wait a moment. Okay. That means now where they have met, that is nothing but the start of the linked list, start of the cycle. So we can just return slow. Okay. So in this thing should work, I think. What happened? I'm saying if fast equals to slow, while fast is not equal to null and fast connects is not equal to null, if fast equals to slow. Okay, so we will actually have to start with, uh, okay, so this thing will be actually initially true. So we actually have to start this because at least we have to move fast and slow ones. Because they will otherwise always be true. Right? Yes. And let us submit. Great. So we did one more question, and today our streak points are equal to 1685. Cool. So that's all for today. See you tomorrow with the day 9 of this. Make sure to complete your streak as well, and we will see you tomorrow. Okay. Bye bye.